today we're going to talk about Pi0, a physical language action model by the company Physical Intelligence. Quickly, let's go over what we do today. We're going to go over our introduction and motivation, what's happening, why did they do it, a bit of the history, what happened, so we're at this point right now. We're gonna go over a case study because it's easier to understand the model when you have a case study. Then we'll really go into the model, really in depth, but still no math. We're gonna go over the results and data and their future work right now. So, what is Pi0? Pi0 is simply a general purpose model that moves robots. That's all you have to know for now. It's simply put the ChatGPT of robotics. That's as far as you should understand to this point. Now we can get into the history. So, this cute robot is about to move this soda can to the image of Taylor Swift. This might seem a small feat, but it might be actually the most significant moment of modern robotics. In fact, one of the engineers working on the project at Google at the time, and this is a direct quote by the way, said that it's the moment he realized this is going to work. This quote is by Carol Houseman, the CEO of Physical Intelligence. Carol Houseman began his story at Google at 2023 when they worked on the RT2 robot, the one I just showed you. Then he took a bunch of his friends from Google at 2023 and left Google to open their own company, Physical Intelligence. When they noticed that this is actually groundbreaking, so let's go and do something. Let's get into the basics so we can understand the model after that. To be able to understand this model, we'll have to understand some of its building blocks because there is a lot of technologies going onto this model. It's built on top of many things. It's not just that, a simple model. We'd have to understand how vision language action models are built on top of vision language models, and how vision language models are, in a sense, built on top of LLMs. We might even sprinkle some robot policies here and there. So let's start with LLMs. We all know what this is. I'm sure we do. Even if we don't understand it fully, but we don't have to spend so much time on it right now. The main things to note here right now is that any transformer using this architecture has an attention head mechanism and then a feed-forward mechanism. And if you don't know what a feed-forward mechanism, yeah, we'll talk about the attention head. But if you don't know what a feed-forward mechanism is, I can't help you. Then Merry Christmas. You're gonna fail deep learning. Let's move on from that to VLMs. VLMs are essentially just LLMs with an image encoder before it, for the image data. It just translates the image data into encodings that the LLM can understand. It's also important to note that those embeddings or those tokens live in the same vector, input vector that goes into the transformer. So the text embeddings and the image embeddings live in the same vector. Now that we understand those building blocks, we can understand what previous models tried to do, previous robotics models, or previous projects at least. This is SEICAM, a previous project by Google also. It's the one before RT2, the robot I showed you at the beginning. The team here used a VLM for the planning, for the mind of the robot, alongside a neural network that was trained specifically to output the robot joint controls, supposedly that moves the robot, with natural language processing as the communication layer between them. The output of the entire model was just the robot control, the robot joint control signals that move the robot. This architecture meant that the VLM had a predefined set of actions to choose from. It cannot choose anything out of them because these are the actions that the neural network was trained on. So for instance, if the VLM was prompted to clean up this spill, After planning its approach, it would come up with some instructions like grab the sponge, move to the table, wipe it down. And those instructions are the ones that the neural network is trained on, and then it can carry them. This brings us back to the RT2 phenomenon, because the RT2 did not do that. The RT2, when prompted to move the soda can to Taylor Swift, it just did it without ever having to train on this type of data or ever seeing this scenario before. This was groundbreaking because the new model actually looked like this. Just one model that takes in image and text input and then outputs directly the joint control signals that move the robot. That was 3 years ago, by the way. Generally, both those models, the older one and the still old one, required heavy compute to work. They required a lot of compute, they had very bad latency. But now we're going to talk about the Pi0, just briefly. It can do so much more than move a soda can to an image awkwardly. It can do your laundry, it can put your food away, it can even open locks with a key. Do you know how hard that is? Compared to the RT2, this is phenomenal. You might actually think that it's a bigger model since it does perform a lot better. But if we compare the metrics here for a second, you can see that the RT2 was a big, beefy 55 billion parameter model that needed a lot of TPUs to work and suffered really bad latency, while the Pi0 is a really cute, small 3.3 billion parameter model that can run on my PC at home with a lot less latency. Now we can get into the model. To understand the model, we will need to look at an example of how it works. This is a good example I found online while doing my research. It would help us understand the model a bit more. This example is about an Aloha robot that had the Pi0 model fitted on it. An Aloha robot is basically just two robotic arms working together on a fixed platform. A big picture view of the project shows us that the Pi0 model can take input from however many images we need it to. We're gonna get into more detail about that in a minute. And text input, and directly outputs the joint control signals that move the robot. It will specifically output 14 joint controls for this specific example when it was fitted on it, because each robotic arm had 7 actuators, so 14 in total. Now seeing the model closely under the hood, we can see that the team decided to build the engine of the model using Pi0, an open source VLM from Google. They worked at Google, so it makes sense before starting their company. So this means that Pi0 was built on top of 2 core technologies. An LLM that is called Gemma 2, it was the Gemma 2 billion parameter model, and the SIGLIP image encoder, which again is in charge of translating the image data into embeddings. Let's use that towards the project we have. The team, when using Pi0, decided to fit the model to the work. They used 3 image encoders, not 1, but 3, because we have 3 cameras. And they moved the input to the input vector from the image encoders, along with the input from the prompt, saying, for example, uncap the pen, and it's seeing a pen here. Following with the RT2 design, you'd think that it would directly now be trained to output the robot joint controls. But that's where the team decided to add an intelligent improvement. They added the action expert. The action expert is a second model inside the model that is concerned with only outputting the joint control signals that move the robot. In fact, if you check the Pi0 code base, you can even see that this model is the same as this model. It's also a Gemma 2 billion parameter model. If you see the code, you can see actually they constructed the model using the Gemma constructor. But wait a second. Do you see what I'm seeing right now? Do you see that this actually looks familiar? Familiar? It looks familiar to the RT2 design, or sorry, the SECAN design, because now we have two models, each in charge of in charge of something. One is in charge of planning, and the other is in charge of doing. Well, they are similar. They are similar in concept, but they are very different in architecture. They even compared the SECAN, this project, to the Pi0 in the paper that we're discussing right now. So this is not an example from thin air. This is an example that was compared to the model in the paper. It is still the case, they do look similar, but the magic lies in the communication between the two models. SECAN failed because it used natural language as the communication between the two models. So if we look at Pi0, since they use the same model, we can actually think of it as one model. They communicate, they have a higher level of communicating than sending data between each other, while still retaining the modularity of having two models. Let's look at each one of them and try to understand each one of them, and then we'll get to how they communicate well together. Essentially, it feels like they are one, so that's where the magic is. Let's first look at Pi0, the one on the top, the one in charge of the planning. As we know, the images get tokenized and move into the input vector. I also encoded the input tokens with colors, so you can see that the orange color denote the tokens that contain the orange color of the pen cap. Also, the text input is tokenized into the same input vector. Remember, we said this would happen. It's on the bottom. They are the two blue tokens for this example. Then they move into the Gemma 2 architecture, which is made up of 18 transformer blocks. Each transformer block has 8 attention heads, and those attention heads are the magic of everything. They are the reason everything works here. So let's actually focus on one attention head and understand what's happening inside there, so we can understand the model better. Let's consider this one attention head from a one transformer block for one iteration of the input. Each attention head has 3 separate weights that are trained and used to multiply the inputs to those weights. Multiplying them produces the query matrix, the key matrix, and then the value matrix. Each row still corresponds to the same patch to the same row in the input vector. As you can see, they're still color coded. The orange one still represents the pen in the image, and the blue ones still represent the prompt tokens. This is where Gemma figures out how to connect the word to the image. So the word pen to the actual pen in the image. From here, this is where Gemma try to find similarities between the query matrix and the key matrix. Those weights, for example, might have trained to prioritize finding similar objects, whether they are in text or in the prompt. So for instance, our example here is pen. So they will try to find, they are trained to try to find the similar objects here and there. The prompt, it will find that by doing the dot product of every row in the query matrix against every row in the key matrix, and then using softmax to smooth out to highlight the higher numbers, where a larger number result means a closer match between those vectors. Interestingly, the biggest results we find in this example, which is in the actual data, by the way, I have references to the data on the presentation, so you can see it later. In this data, interestingly, the prompt in the query vector saying the word pen matched really highly with the actual patches of the image that have the pen in them. This is done for all the values in the matrix, by the way, but this is the highest, largest numbers we got. The results of those matrix multiplications and the softmax operation is put into this resulting matrix called the attention pattern. Now that our attention pattern represents the query matrix and its relationship with the key matrix, it's put inside their place with the key key matrix, and then it's multiplied by the final values in the value matrix to give us our final attention heads output. This is the final output of the attention head. This essentially represents the relationship between what's in the prompt and what's in the image and where. Now remember, my friends, this was just one attention head for one input sample, for one time step, for one transformer block. We're gonna do this for all the transformer blocks, for all the attention heads. Now that we get how JAMA works, we can go now to the action expert. Let's consider the action expert alone. Since we said it's the same as JAMA, it should be the same architecture. And it is. In fact, it is the same architecture, but not the same input. That's where it's different. The input for this input vector is the actual position of the 14 actuators in our both robots' arms, multiplied by a learnable, trainable weight, and put into the first vector in the first row in our vector input vector. Next, what's put in there is the next 50 positions of the robots. So the future 50 positions are put into the input of the action expert. You should be really weirded out right now because this is really weird. How do we know the next 50 positions? Well, we don't. If you were weirded out, I'd say that you were correct. It was weird to include them because that's the whole point. That's what we're doing here. We're trying to predict or say to the robot where to go next. So how do we input the next 50 positions? Well, the answer really briefly is a bonus segment in this presentation, GAN networks. For whoever knows GAN networks or who doesn't, this is pre-attention generation techniques. A GAN network or a generative adversarial network is a network that we learned about during the old days of pre-attention. I learned about it in my bachelor's. Simply, it's an image generation technique or an image generation model that uses two models inside. It uses one model to start off with fake noise, random noise, and try to create a fake image using this noise. Try to move the noise in the image towards being like an image that was used in training. And the discriminator model is like the police on the other side. It's like a game of chasing with the police. This model is the discriminator. It says if the image is real or fake. If it says it's real, then it passes. It learns that this is a good output. If it says it's fake, it goes again and tries again to generate some more random noise towards looking like an image. We can actually see it here. This is an image of random noise, and one by one, it starts to look better and better. Sorry, this is slow. I don't know why this is slow. Yeah. Oh no, this. I'm sorry, I'm experiencing something. Yeah, here it is. It moves the noise in the image towards looking like an actual image. It's a nifty little technique that the team borrowed from image processing. We can see it at work here in this very similar image. I would say it's not an image. When the team does it here, it's called flow matching. The action expert shapes the random noises. Let's say we have the random next 50 positions or random noise. This is the x-axis as 50 and multiplied by 14 actuators. It starts with a smooth trajectory moving from here to here. You can see the model is telling the actuators to move towards the pen. So yeah, that's what it is. We start like this with random random 50 steps, and we put it in the input. It moves to the action expert. The action expert tries to improve it. At first, of course, it produces some noise, and after a while, it's better, and it's moved to the input, and continued for exactly 10 steps. Now that we have a good looking plan by the action expert to move that way, we can move. But how did we reach this plan? We don't know anything about where the pen is. Remember, this is the action expert. It doesn't have any information on what's the Gemma up, the other model is looking at. Well, this is the cool part. We will have to look at how the action expert works under the hood to understand. Looking deeper, since we know its architecture is the same as the Gemma 2 model, we would look at it and it looks the same. Let's look at one attention head from this transformer block in the action expert. Before we get into the attention head, we can put both models in the same space so we can understand that they are very similar. This is the output at the end, and now we can look at the action expert, at the attention head of the action expert. It's just another attention head doing its thing. As you can see, the first, it's still color coded as the Gemma one, as the first Gemma one. Those are the 50 next ones. This is the current position. It's very normal. It does its thing. But this is where we see the genius of having the same architecture for the two models. Let's put them side by side. Let's put the attention head of the first Gemma against the attention head of the action expert. Since they have the same architecture, this design enabled the team to share the key and query values of the first Gemma with the action expert. Sorry, the key and the value matrices with the attention expert. It would look something like this. They would put them all in the same space, and this is the smart part. Now the action expert has a full understanding of everything that this Gemma model is seeing in the same space. So that's how it knows where to go and why to go this direction. They essentially think as one. This can only be done if they are both the same architecture. Of course, there are a lot more details to be covered here, but we're not gonna go over that now. Now we can go over the results and data and how they treated their data, because it's still a large language model under the hood. So supposedly they did something different to be able to get this output. Well, the team treated the model just like any transformer, actually. They set up a huge amount of pre-training on general purpose stuff, just general actions. And as you can see here, they trained on dryer unloading, mobile laundry, table bussing, laundry folding. And this is the results before and after fine-tuning. Because it's a general purpose model, it should be able to do stuff without having to be fine-tuned. And it did perform very well without fine-tuning on the trained on general purpose actions, and after fine-tuning it did so much better on the actions that it was never trained on, actions that it never saw before. They trained for 10K hours of data points over 7 different robots, and for 68 general tasks. Right now they are on Pi 0.07. That's where they are now. They improved a lot, and we don't have time, unfortunately, to go over that right now. But it's the